Hi everyone, this is our first video for our depth study where we're making our tubulin. One of the questions that we are reflecting on comes under the category of understanding air columns, and it's this idea of how sound propagates through air. Now, just building on what we've already covered in class, there's a couple of things that we need to consider. So we've modeled longitudinal waves as a type of a mechanical wave which uses a medium. In this particular instance, we're talking about the air or the gas for a particular atmosphere. And what happens is, if we model the compression regions as being places of high pressure, where the pressure exceeds that of the atmosphere, where the atmosphere would be this neutral point here, and that will correspond to this section here in the longitudinal wave. Then our refraction area over here, well, that represents our low pressure region. So it's almost like a void or less of the pressure that happens in the atmosphere. It's important that we describe those regions because what happens, in order for us to understand how sound waves propagate, we have to understand how these pressure regions relate to one another. So what happens is, when you impart some kind of energy onto the particles which make the air or the gas that makes that particular atmosphere, that energy creates shock waves where there are certain regions of high pressure which particles tend to coalesce or come together, and then that is followed by a region where the particles are more loosely represented and they have more ability to move back and forth, and that's beyond what they normally are found in. So somewhere in the atmosphere you'd find the particles being in this kind of region where they're just kind of homogeneously distributed. But when you actually apply a sound wave, that's what's happening. It's almost like a accordion or some kind of creature which kind of brings itself together and stretches itself back out. It's moving back and forth. It's almost like it's crawling through the air using the molecules which make up the air in order to do so. Now, we've used a FET simulator in class to illustrate this. And it goes like so. So we got a speaker here, and what we could do is see how that appears when we actually create a pulse. Okay, so we create a pulse, consistent pulse, and we can see as the membrane of the speaker retracts, it creates a low pressure region, which is denoted by the black concentric circles, and the white concentric circles tend to be the high pressure. So that'll be our compression, and our blacks will be our refractions. Now what we can do is we can have both the particles and the wave to illustrate that. So you can see during a high pressure region, that red particle oscillates towards the source, and during a refraction, the lower pressure regions, they tend to go back. Now that continues on back and forth, back and forth. Now, because of the conservation of energy, the law of conservation of energy, that energy will dissipate eventually with all the different forces that are already present in those particles, so that energy does get lost, so that sound doesn't continue on forever and ever. But that's effectively what's happening. You got a high pressure region that's created, that's followed by a low pressure region. That's by definition a sound. Otherwise it wouldn't be a sound. It'd be just a shock wave that moves at a certain pressure all the way through. And that's not what happens with sound. With sound is you need to have an actual compression and a refraction. And that's the smallest sample of a noise that you can create, a wavelength of a noise. Okay, now before we talk about speed of sound in gases or in the atmosphere, we need to consider what this idea of kinetic energy. Now, kinetic energy is got its own uh, representation, but what it tends to generally mean is it's usually got to do with the energy that a moving object possesses. Now, here we've got to think about the general energy that molecules in a gas possess is given by this particular expression. How this expression is derived is not of an important concern yet, and nor for the HSC physics course. But a couple of constants do arise here, which are important and will come up later. So this Boltzmann constant, dealing with the variable k, that's quite an interesting constant because that relates the amount of energy a particular molecule will possess on the basis of the temperature it experiences. It's a very important constant, and it's this idea of quantizing energy. Now that's going to come up soon, but that basically has to say that every increment of temperature that a particular molecule experiences increases by this proportionality constant, which navigates how much energy is imparted to that molecule. Now remember that kinetic energy is mainly got to do with the speed experienced by that molecule. So let's have a look at that in more detail. Okay, so here we got some molecules that have been um, entered into a into a particular chamber. Now these molecules themselves, they have a particular speed. You can see they're denoted by some kind of average speed, and they tend to be in the lower range. You've got some that are very fast and some that are very low. Now these are quite interesting because they marry up with how much kinetic energy those molecules are experiencing. And that distribution of kinetic energy resembles very similar to that speed. So again, that goes with this idea that whatever speed those particles or those atoms or molecules are experiencing is related to how much energy those particles have. Now what happens is if you start heating those particles up, okay, you can see our temperature is rising quite dramatically there. We got some more speed being experienced, and again, that overall kinetic energy has been distributed more towards the center here, and we're starting to see some particles with some large amount of kinetic energy. Now we can make this a bit more visible by adding more particles in there, and then again, there you go. So you can see that average is still increasing a lot. So we'll add some more heat in there. You can see as well, look how fast these particles are moving. So you can see there's a direct correlation between heat and how fast those particles are moving. Okay, now this is the expression that we're talking about. This relates the speed of sound in a particular gas. Now, this is an expression that is beyond the scope of this syllabus, but it's important that you understand how these variables again overlap. So you can see again, you got the term for temperature appearing again. Now, what you got to be conscious about is whenever we're dealing with temperature, they're represented in units of Kelvin. Now, a Kelvin is basically, 0 Kelvin is basically the temperature where atoms or molecules cease to do any form of movement. That's minus 273.15 degrees Celsius. So the equation for converting back and forth between the temperatures is that. So if you got degrees Celsius and you want to convert to kelvins, you have to add that factor in. And again, if you got kelvins and you want to go from kelvins to degrees Celsius, you got to subtract 273.15 from that number to get its equivalent in degrees Celsius. The other thing I want you guys to notice here, a couple of constants come up. So you got the universal gas constant, which deals with the amount of the amount of kinetic energy a particle has with respect to the temperature that it experiences. Now, you got this other constant here, which we call the adiabatic constant of the gas. This is an interesting constant because this one deals with the exact quantitative change of heat energy added, which manifests itself into kinetic energy. So they're quite different in that respect. Now, this over here, that's molecular mass of the gas. If you look at the composition of Earth's atmosphere, we got nitrogen gas accounting for 78%, oxygen gas 21%, argon 0.93%, carbon dioxide 0.03%. Now, each one of these substances has a particular molecular mass it has. So the units are how many grams of that would be found in a mole. Now you can see obviously the bigger molecules, so here we got carbons and 2 oxygens, you can see they've got a bigger mass, so all those different atoms have to be considered in that mass. Now the reason why you get a distinct average mass in the atmosphere is that all these are considered in terms of the percentage. So even though carbon dioxide's got a humongous mass compared to say the nitrogen gas found, you can see that that accounts only for 0.03%, whereas the nitrogen gas is 78%, so that would be represented more. So when you add those masses with respect to the percentage found in a particular volume in the atmosphere, it gives you an average molecular mass of 28.95. So that's interesting. So that also, so the larger the gas, the heavier the gas, the more of an impact it's going to have on the sound, right? So if you've got a really heavy gas and the denominator there, you can see that that speed is going to be significantly reduced. And that's not what we want. So if you have something really light like helium gas or hydrogen gas, you can see that that smaller number is going to make that numerator increase, which you can see here, these are constants. It's just the temperature. So depending on how much you heat that gas, that sound is going to be traveling quite fast. So let's look at a couple of examples here. Okay, so here we got air at 0 degrees. So that's at 273.15 kelvins. You can see that's the speed, 331.5 meters per second. Now we can actually simplify that condition a bit. So we've got a couple of values here. So we got our adiabatic constant here for our atmosphere. We got the gas constant, and we got the average molecular weight of the atmosphere, and we've entered those values in, and we've actually left the temperature outside, and we've simplified them. So we end up with this particular equation here, and we can examine for what would happen at 25 degrees. So just by heating the atmosphere up a little bit, or the environment, you can see that that speed has increased significantly, 351 meters per second. Again, this is more about explicitly seeing how the variables relate rather than you having to use the equation to work anything through, because this doesn't appear in our syllabus. Okay, so let's look at how these waves, standing waves, are formed in our air columns. So here we got an open pipe, we got both ends are open, and what happens is we got a particular wave that has been imparted into it. You got your compression and you got your refraction over here. The compression being the place of high pressure and the refraction being the place of low pressure. So what happens is as that wave propagates through the pipe, it's constantly colliding with the sides of the tube, and it's reflecting back on itself. So you're maintaining this perfect shock wave as it's going through, composed of a compression and a refraction. And what happens is once you get to the open end, that that compression phase, what happens is because it's high pressure, it dissipates into the middle pressure atmosphere. And what happens is it almost sends a shock wave or a ricocheting of the refraction phase, and that goes all the way back down the pipe, right? So it's almost like a compression phase never existed once that pipe, once that the phase of that wave gets reflected back. Now what happens, the interesting thing is once that low pressure refraction gets to the other end, what happens is the atmosphere, which is slightly higher pressure than the refraction phase that's coming out, what happens is that quickly oozes into that area and it creates another compression phase. Now that compression phase obviously is going to be, it's not going to be the same amount of strength as the original one. So again, it comes back to this idea of the conservation of energy. Some of this energy has been lost into the environment. Now ideally, in an ideal situation in this particular model, that compression phase would be equal to the initial one, but that's not the case. But anyways, as that refraction gets to the open end, the air from the outside, the medium pressure air from the outside rushes in. It fills that low pressure refraction. It creates another compression wave, and it starts heading back down, and the cycle continues on. High compression dissipates into the environment. The refraction phase is shot back. And what happens is when these progressive waves continue to occur in the pipe, they constructively and destructively interfere in a certain way, where you create a high pressure area in the center of the pipe, and during the outer open areas of the pipe, those become the low pressure regions, right? So we already have names for these. We know we call these ones our nodes, and we call them our antinodes. Now this can be represented more clearly using these transverse wave diagrams. And what we can see is that the antinodes are indicative of our low pressure region, and our nodes represent a high pressure region right there. Now this is a bit different in our closed air columns. So what happens here is you can see we got our closed ends over here marked by the light blue. So what happens in this situation is once that wave enters the pipe, that compression phase that hits the closed end of the pipe, that doesn't get reflected back as a refraction. No, that one actually gets reflected back as a compression wave. And what happens is once that wave that was being sent down the pipe gets to the open end, the same thing that happened in the open pipe occurs. So what happens is that high compression region dissipates into the middle pressure environment, and then you get a refraction wave being sent back. Now that refraction wave will hit the closed end of the tube and again be reflected back as a refraction wave, and will create another compression wave once it gets to the open end again. And that will continue back and forth. Now this one is quite interesting because what ends up forming is this. You get a high air pressure region forming at the base where the closed end of the pipe occurs, and as you get towards the open end, that's where our low pressure region happens. And we can represent that as a transverse wave, and this is more how it's going to look like. So again, you get one node forming at the closed end of the pipe, and you get an antinode at the open end of the pipe. Now these waves look quite differently, and we'll talk about their actual size in the videos to come. Because yes, they are waves that are formed, but you can see that their sizes are quite different, and that's going to be very important in determining how they sound and what frequency they experience or resonate at.